In this next video, we'll continue with exercises of implicit differentiation, but this time we want to learn how to evaluate the derivative of an implicitly defined function at a particular point, at a given point. So let's look at 21. We'll go through the odds here. And we will use a slightly different strategy when we're evaluating an implicitly defined function or the derivative of an implicitly defined function at a point. So for 21 we have x times y equals x equals 6. We'll start by taking the derivative of both sides with respect to x. On the left side we have this famous product, the derivative of the famous product xy. So that's xy prime plus y, as we've seen before. And it's equal to 0 on the right side. When we're trying to find the derivative of an implicitly defined function at a point, I would stop after the calculus is done, after the derivative has been found, and plug in the x and y values that were given. So that would be -6 and -1. I hope that's clear. So we set x equal to -6, y equals to -1, and all we're going to do is solve for y prime now without simplifying algebraically first. So -6y prime equals 1 and y prime equals -1/6. Okay, we'll go on to number 23. In 23 we have y squared is equal to x squared minus 49 over x squared plus 49. So we have a couple of things that are going to make this challenging here, and the first one is obviously the quotient rule on the right side. We'll take the derivative of both sides with respect to x. On the left side we'll get 2y y prime, and on the right side we'll have a simple quotient rule in terms of x. So it's low d high, which will be 2x, minus high d low, which is also 2x, divided by low squared. Alright, so that's a lot to be simplifying there. However, the calculus is done and we can begin to plug in the points that we have. The good thing is that the y coordinate is 0, which is going to produce something kind of interesting here. When we plug in y equals 0, the whole left side is going to become 0. And that indicates that the derivative is not going to exist anywhere. It's a very interesting phenomenon. We'll see what that means. On the right side though, we can begin to plug in x equals 7 in each case. So rather than go through the trouble of simplifying this all. Now one thing we'll notice about the right side of the numerator is that 7 squared minus 49 is going to be 0. So the whole right piece goes away there. And that leaves us with x squared plus 49 times 2x over x squared plus 49 squared. And we can cancel one of the x squared plus 49's in the numerator with one in the denominator. And that should just leave us with 2x over x squared plus 49. However, when we plug in 7 for x there, we're going to get 14 over 98, which can't equal 0. So that means that this doesn't exist, or that it's impossible. So this is a strange kind of function then, or a strange equation that has no derivatives anywhere. So let's see what that means, or see if we can make some sense of what we have here. So what I'm going to do, or what I've done, is I've used one of my favorite graphing programs called winplot.exe that you can download online, winplot.exe. You can Google that, download a copy of it, and it allows you to graph implicitly defined functions. And when I do that, you can see why at the particular point we're given, which is x equals 0, y equals 7, or rather, sorry, x equals 0, y equals 7, that the derivative is undefined there. It happens to be a vertical tangent at that point. And you can see that over here, when x is 7, y is 0, we have this vertical tangent in here, and so it makes sense that it wouldn't be defined. So I'm going to close down this graph. And what I said before was that the derivative didn't exist anywhere, but that's not true. When we plug in the point x equals 7, y equals 0, the derivative doesn't exist. And that was confirmed by looking at the graph and seeing that at that point there's a vertical tangent there and the derivative won't exist.